Imagine a planet more than twice the size of Earth orbiting a red dwarf star. Its atmosphere is thick with hydrogen and helium. At first, it looks like a miniature Neptune, but underneath its atmosphere lies an ocean that's unlike anything we have on Earth. This ocean spans the entire globe, and it's hot, nearly twice the boiling temperature of water on Earth. But on this planet, the water doesn't boil away because the atmosphere bears down hard on the ocean, driving pressures to nearly 10 times what we feel on Earth. It might seem like such a planet would be entirely inhospitable to life, but a team of astronomers at Cambridge University found that planets like this one could be habitable for heat-loving microorganisms called extremophiles. The astronomers call such planets Haitian worlds, that is, ocean planets surrounded by thick hydrogen atmospheres. We have nothing like them in our solar system, but they're among the most common types of planet in our galaxy. You might think, well, that sounds interesting, but it's going to be decades before we have a telescope capable of detecting life on other planets. Well, that would certainly be true if we constrained our search for life to small terrestrial planets like Earth. But if these astronomers are right, the James Webb Space Telescope may detect life on a Haitian planet in just the next few years. Welcome to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer, and today we're talking about how Haitian planets will expand our search for life beyond Earth. Now, if you're curious about the search for life like I am, I'd like to take a moment and recommend a mini-series called Life in Outer Space, which is available on Magellan TV, who I'd like to thank for sponsoring today's video. Part 1 of Life in Outer Space talks about the search for life in our solar system, such as in the permafrosts of Mars, the oceans of Jupiter's moon Europa, and Saturn's moon Enceladus. It even explores the possibility of finding life in the methane lakes of Titan. Part 2 explores the search for life beyond our solar system, the discovery of exoplanets, and the methods by which astronomers could detect life on them, whether by finding biomarkers in their spectra or even signals from alien civilizations. This series, and many more like it, are available on Magellan TV, which features more than 3,000 titles on nature, history, space, science, and technology, with new documentaries added every week. I think you'll find Magellan just as inspiring and enjoyable as I do. And best of all, Magellan is giving my viewers an extra month of their award-winning content absolutely free. You can claim this offer by using the link in the description of this video. In 2019, the Hubble Space Telescope detected water vapor in the atmosphere of the exoplanet K2-18b. The planet was discovered 4 years earlier by the Kepler Space Telescope orbiting a red dwarf star 110 light-years away in the constellation Leo. So when Hubble detected water vapor in K2-18b's atmosphere, it was kind of a big deal. In fact, it was the first time water had been detected on any exoplanet. Granted, the presence of water vapor alone doesn't prove that a planet is habitable, let alone the presence of life. But as far as we understand, life requires liquid water. So if there's water vapor in K2-18b's atmosphere, what's the rest of the planet like? Well, K2-18b is about 2.5 times larger than Earth, and that puts it firmly in the size range between Earth and Neptune. And we don't have anything like that in our solar system, but most of the exoplanets out there fall into this range. And these planets are thought to have compositions ranging from rocky super-Earths with relatively thin atmospheres to low-density mini-Neptunes, which are thought to have large atmospheres of mostly hydrogen surrounding a liquid water ocean. Kepler's observations indicate that K2-18b is about 8.6 times Earth's mass and is about 2.5 times larger. And that gives the planet a bulk density of about 2.7 grams per cubic centimeter. Now that's a higher density than Neptune, but it's still quite a bit lower than Earth's. So K2-18b is probably a mini-Neptune instead of a super-Earth or even an ocean planet. Unfortunately, early studies of mini-Neptunes found that while they would have liquid water oceans, their heavy atmospheres would drive the pressures and temperatures at the ocean's surface much too high to support life. But armed with data from both the Hubble and Spitzer space telescopes, astronomers could narrow the range of possible conditions that K2-18b could have. A team from Cambridge University, led by Niku Madhusudan, did just that. They found that some of the allowed temperatures and pressures at the planet's surface could be low enough for life to survive in the ocean. In other words, K2-18b could be habitable. Now, by habitable, I don't mean like anything we would find tolerable, such as the conditions here on Earth's surface. But we know that life does just fine around hydrothermal vents at the bottom of the ocean. Their water temperatures can reach up to 464 Celsius, but instead of vaporizing, the water remains liquid thanks to the pressure of the rest of the ocean bearing down on it. It doesn't matter if the water is highly acidic or highly alkaline. Life thrives in these extreme environments. We call such life extremophiles. But even these habitable conditions are only a portion of the possibilities allowed by K2-18b's data. At one extreme, the planet's hydrogen envelope could be as much as 6% of the planet's mass. That's more than enough to drive the surface pressure to well above habitability. But most of the solutions required much less atmosphere. In fact, some scenarios required so little hydrogen, the pressure and temperature at the water layer could actually be closer to those here on Earth. And that would make K2-18b an ocean world with pressures around 1 bar and water temperatures around 27 Celsius. Now, chances are K2-18b has an atmosphere that's thicker than this minimum range. So at best, we're probably looking at something much hotter and under higher pressure than a super-Earth or even an ocean world. But it's quite likely not as high as that of a typical mini-Neptune. If so, K2-18b could be quite habitable for extremophile life. Well, that got the team wondering. If K2-18b was a potentially habitable mini-Neptune, then there should be a sub-range of mini-Neptunes that could also host life. The team dubbed these worlds Haitian planets, that is, a habitable ocean planet surrounded by a hydrogen atmosphere. The team went to work calculating and modeling the different combinations of planets' mass, composition, and distances from the host stars that would still result in a habitable Haitian planet. They found a range of temperatures that these planets could have and still be habitable. So, a typical Haitian planet might have an ocean surface temperature around 200 degrees Celsius under about 3 bars of atmospheric pressure. Again, lethal for us, but nothing that Joe Extremophile would object to. Next, the team looked into the range of distances the Haitian planets could have from their host stars. In other words, they wanted to figure out what was the Haitian habitable zone. Well, this range depends on the star's temperature. The hotter the star, the farther away this zone is, and vice versa. But it also depends on the planet's properties as well. For terrestrial planets like Earth, the relatively low surface pressure means that liquid water is confined to a fairly narrow range of distances from its host star. But the team found that thanks to their thick atmospheres and internal heat, Haitian planets can remain habitable to as far as 12 AU from a Sun-like star and as close to 0.01 AU for a small red dwarf star. That alone is really interesting. However, we know that planets can get much, much closer to their stars. When that happens, tidal forces from the star slow the planet's rotation down until it matches its orbital period. The planet becomes tidally locked, with one side always facing the star with the other in permanent darkness. With a never-ending onslaught of radiation from the nearby star and internal heat pumping into the ocean, the day side of these planets would eventually become too hot to sustain life. But on the dark side, things could be quite different. There, the ocean is warmed by the planet's internal heat, as well as the energy flowing from the day side. Could this be enough to make the dark side habitable? Well, to find out, the team took a conservative approach. They modeled these planets assuming a very inefficient energy distribution. Even then, the team still found an additional dark Haitian habitable zone that gets considerably closer to their stars. And that's really good news because there's a number of possible mini-Neptunes that fit within this new habitable zone, including some possible Haitian candidates. The team also considered Haitian planets with little to no starlight at all. In other words, planets that orbit very far from their stars and even free-floating planets without a star. In this scenario, the only energy source for the atmosphere is the planet's internal heat. They found that depending on the planet's mass, radius, and internal temperature, cold Haitian worlds can maintain habitable conditions down to a frigid -3 degrees Celsius and an atmospheric pressure of 1,000 bar. And that's pretty much the extreme limit for cold-loving extremophiles on Earth. But if the planet has a slightly higher internal temperature, then life could swim in warmer waters at lower pressures. It's amazing to think about a rogue planet drifting between the stars, yet carrying with it life. Now, to be clear, these models don't make any prediction of life on Haitian planets. They only predict a range of possible conditions that are otherwise sustainable to microbial life. And therefore, we shouldn't expect to find evidence of large Haitian whales or other intelligent creatures broadcasting messages to us, although that would make our jobs a lot easier. But if one of these planets had microbes swimming in the oceans underneath thick hydrogen atmospheres, would we be able to detect them? Well, let's take a look at the atmosphere. If we took a direct spectrum, we'd expect to see absorption due to hydrogen, helium, water, and probably methane and ammonia, none of which are necessarily proof of life. So what else might we find? Well, traditional biomarkers such as dimethyl sulfide, carbon disulfide, chloromethane, carbonosulfide, and nitrous oxide have been proposed for both rocky and terrestrial planets as well as for hydrogen-rich atmospheres. However, it might be easier to detect these biomarkers in Haitian planets rather than in the atmospheres of super-Earths for two reasons. First, Haitian atmospheres are thicker, but their surface gravities are lower, allowing the atmospheres to grow taller. The larger and thicker the atmosphere, the more biomarker absorption we can detect. Second, the biomarkers in question are thought to come from aquatic microorganisms, and these planets are nothing but oceans. Without any annoying land masses in the way, these microbes would have the entire planet to themselves, belching their biomarker gases into the air. So on the one hand, biomarkers should be easier to detect on a Haitian planet than on a rocky super-Earth. But would it be easy enough for the James Webb Space Telescope to detect? Well, it would be great if Webb could just take a direct spectrum of the planet, but that's not going to happen. Even though K2-18b orbits a small red dwarf, it's much too close to its star for Webb to directly distinguish. But in the last few years, astronomers have come up with a clever trick. Instead of trying to take the spectra of an entire planet directly, astronomers take two spectra of the same star. Once when the planet is out of its way, and once again when the planet is transiting in front. When the star's own spectrum is subtracted from the combined spectrum, what remains is the spectrum of just the planet. This is a technique called transit spectroscopy. Given what's known about K2-18b, its host star, and Webb's capabilities, the Cambridge team calculated what the planet's spectrum would look like to Webb if it had biomarkers in its atmosphere. They simulated observations taken over 3 transits of the planet. Sure enough, absorption lines from biomarkers were present in the resulting spectra. They even repeated the calculations for 2 other Haitian planets and got very similar results. This is why I'm so interested in these Haitian planets, because if these models are correct, and these planets really do turn out to be Haitian worlds, and if any of them have life, Webb could detect it. Granted, there's much about Haitian planets and habitability that we still don't know very much about, particularly when the planet orbits close to a red dwarf star. Are their atmospheres really strong enough to minimize UV radiation from the star? Are the magnetic fields strong enough to withstand flares that are up to 10,000 times stronger than those on the Sun? Would Haitian planets recycle atmospheric gases to regulate their temperatures, or would they eventually lose their habitats to a runaway greenhouse effect? Well, there are a range of possible answers to these questions, and the majority of exoplanets are within the size range between Earth and Neptune. And this study allows us to expand our search for life into this mid-sized planet region. Not only are there more of them out there, but they could support life over a wide range of distances from their stars. But most importantly, we may actually be able to detect life on a Haitian planet with the James Webb Space Telescope. Say what you want about how long it took to build, but it's going to start studying exoplanets within its first year of operation. Imagine if we detected life with it in the next 5 years instead of the next 50. I think that might make it into the papers. I want to thank my Patreon supporters for helping to keep Launchpad Astronomy going, and especially for helping to give me the time to study and research videos like this. And speaking of videos like this, if you want to stay up to date on the latest developments with new planets and the James Webb Space Telescope, well, make sure that you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay curious, my friend.